Siddhyo Mentor Vilas Sarkar. Now we'll continue from the part which we have left on 30 number. The second part of this, that there we have to prove that B plus C into A is equal to BA, and for that this matrix is given. So we'll start with the left hand side where B plus C will do first. So and then we will multiply it with A. So B plus C, what is the matrix we'll get is -2, -1, 1 and then 2. And if we multiply it with matrix A, then this has to be multiplied with this. So so the matrix will become -2, 1, -2 plus 0, -1 into 0, 0, -2 into -2, that is equal to -4, 1 -1 into -1 plus 1. Then second row, 1 into 1, 1 plus 0, and 2 into 0 is 0, and then 1 into 2, 2, and 2 into -1, -2. So this will become how much? -2, -3, 1 and 0. This is the final form. So we'll keep it somewhere so that we can remember. So this part only as a left hand side result, I am writing it here so that we can compare later. Now the second part is that we have to do BA and CA. So BA, what do you find? BA is equal to 0 into 1, 0, 1 into then 0 into 1, 0, -1 into 0 is 0. So this total is 0. Total is 0. Then after 0 into 2, then 0, -1 into -1 is +1, 1. Then after this 1 into 1, 1, and 1 into 0, 0, so the total is 1. 1 into 2 is equal to 2, minus 1 into -1, that is equal to -1, so ultimately it's 1. Okay, this will be the case. And CA will be how much? This into this, -2 into 1, -2, and then the second part is 0, 0, -2 into 2 is equal to -4, then 0 is equal to 0, and then the second one 0 into this one 0, 1 into 0, so total is 0, then 0 into 2, 0, 1 into -1, -1. Now you add up these two. If you do BA plus CA, if you add, so what will be there? -2, -2, 1, this will be -3, 1, 0, 1, -1 is equal to 0. So you can compare it, these two matrices. This is your right hand side, the right hand side and left hand side, both matrices are same, so hence we can prove it. Okay, so now we'll move on to the 14th problem. Okay, so let's see what is waiting for us. So number 14. Okay, so number 14, earlier we have proved that the multiplication is your commutative. Now there is another more problem. There we have to see the now earlier we see that the other way around, if the matrices orders are not same, then if it is possible to multiply A into B in case the column of the first and the row of the second are the same. But if you reverse it, if it is a irregular order, means there is that is not the square matrices, then multiplication is not at all possible. But in this case, what we are taking right now is a square matrix where the other way around is possible, but there could possible that the result are not same. So that we have to check. So this is one matrix, and this is another matrix. Okay, now both the multiplication, whether we do A into B or B into A is possible, but we have to check whether AB is equal to B or not. So first we will move with AB. So 5 into minus 1 minus 5, 2 into 3 plus 6, 5 into 2 10, 2 into minus 2 minus 4, sorry, minus 4. And the second line is 2 into minus 1 2, minus 2 minus 3, minus 2 into 2 minus 4, minus 4 minus plus. So this is your 1 6 minus 1 minus 2. So this is AB, and we'll calculate BA. So then minus 1 into 5 minus 5, 2 into minus 2 minus 4, minus 1 into minus 1 into minus 2, 2 into minus 2 minus 2. So this is over 3 into 5 15, minus 2 into minus plus 4, 3 into 2 is 6, minus 2 minus 2 plus 2. So you can see definitely that result is not matching at all with the earlier result. Okay, so this is the ultimate. So we can say that even if the multiplication is possible, as although the matrices are square matrix of 2 into 2 plus 2 order, so even if it is multiplication possible, but the result is not the same. So we can say the matrices are not commutative. Okay, so this is your can say conclusion. So the next problem will take it up, number 15. Number 15. For these matrices, we have to prove some. For A is given as 0 1 1 1, then B 0 minus 1 1 1. So these are two matrices are given. You have to prove that A plus B for these matrices A minus B is equal to A square minus B square. This is stand true. Okay, so this is very straightforward. What you have to do, A plus B you have to find, A minus B you have to find. So let us start with A plus B. All this we will find first, then we will go to see whether left hand side and right hand side are equal. So A plus B means 0 0 2, this is also 0 0 0 2 and 2. This is A plus B. A minus B 0 minus 0 0 1 minus, this is 2, this is become 2 1 minus 0, this is 0. So this is A minus B, and we will also find A square. So that means this and this square. So what is that? 1 0 into 0 0, 1 into 1, that is equal to plus 1. So this is total 1. 0 into this is equal to 0, 1 into 1 1. So then the second line, this into this first 0 and 0, this line second. So this is equal to this into the first line, second line into first line, 0 into 0 0, and 1 into 1 is equal to 1. So this is also 1. Now the second line, 1 into 1 is equal to 1 plus 1 into 1 is equal to this will become 2, isn't it? So we'll start with this. This into first line will vertically move, vertical. So 0 into 0, 1 into 1 1, 0 into 0 0 into 1 0, 1 into 1 1. So second line, this into this, 1 into 1, and I am not mistaken somewhere. This is the same matrix we are putting one after one. 0 into 0 0, 1 into 1 1, 0 into 1 0, 1 into 1 1, 1 into 0 0, 1 into 1 1, 1 into 1 1. This is right. So B square is equal to, similarly what we have to do, we have to keep like that, minus 1 and minus 1. So what will be my result? 0 into 0 minus 1 minus 1, 0 into 1 minus 1 minus 1, 1 into 0 1 into 1 1, 1 into minus 1, 1 into 1 0. So this will be the case. So now what we have to do, this is this into this, so a plus b into a minus b first we have to do. So for that we have to keep this side by side, 0 2 0 0. So result will be 0 0 0 0, this will be 0, this 2 and this is 0, again 0, this 2 into 2 4. This will be the case. Now here a plus b, a minus b, here we have to do a square minus b square. So what is that? This minus this, this into this, you have to multiply 0 into 0, 0 into 0, 0, 0 into 2, 0, 0 into this also 0, 2 into 0, 2 into 0, 0, 2 into 2, 4, 2 into 0, 4. So this is 0. So 1 minus this is 2, 1 minus this is equal to 2 again, this minus this is equal to 0, 2 minus 0, this is 2. So this is not standing true. A square, you have to prove it. So I am doing something wrong. And let's check the matrices. 0 0 1 1 0 minus 1. So this is 15 number. What he did, a plus b, this plus this is equal to 0, plus minus 0, 2 2, a minus b 0, 2 minus minus. So this is okay. So if I multiply this will become 0 into 0, 0 into 0, 0. This is also 0, this is 0, this is 4. This is correct. A square, let me check once a square how it is coming. This math we have to check once. 0 1 1 1, 0 1 1 1. So this becomes 0 0 1, 0 1 1 0 1 1 1 2. B square, then b square will be 0 minus 1 1 1, 0 minus 1 1 1. So then is equal to 0 0 minus 1 minus 1 minus 1, 0 0 minus 1 minus 1, 1 0 0 1, 1 minus 1 1 0. Now if we deduct it, a square minus b square, this will become this minus this 2, this minus this 2, this minus this 0, this minus this 2. So this is coming. Now if I take even 2 common, so this will become 1 1 0 1, and if I take 4 common, this will become 0 0 0 1. So matrices, if I expand it, okay, let's say expand it, so this will be 2 into 1 2, and this will become 0. So how it is same? It is not same. Let me check the result. Yeah, this is not equal to same. A plus b is equal to us coming plus b is coming okay. So anyhow, the sum is correct. So here you can see that a square minus b square is not equal to a plus b. So this is not following the algebraic rule of algebraic rule of your what you can say, the algebra of algebraic rule is not being followed in case of matrix. So that is proved. So in algebra, what we can say, a plus b into a minus b is equal to a square minus b square for any numerical value. As we can say, if it is 4 and 2, a and b, so then 4 square minus 2 square is equal to 4 plus 2 into 4 minus 2 as it, but in matrix it doesn't follow. So that we can prove by doing computation of these matrices. Now we'll move to the next problem, that is number 16. The next problem that we have to show that any variable x plus a, these are our matrices. This is also matrix. These all are matrices. I mean, this is individually matrix. This is matrix. This is matrix. So for this case, whether this will follow the equation rule of algebra, that we have to prove. And another one is if, yeah, this is second one part. This is second one. If what is said, 3x is equal to a, then x is equal to 1/3 of a. That we have to prove. These are no need of having the exact matrices, because if you see literally, physically, when we do plus or minus, there is no change in the order of the matrix, and there is no change in the orientation of the matrix. Orientation of the matrix will be same, and the order also same. Because multiplication, your multiplication process is you are multiplying rows to columns, so there is a chance of changing more orientation. But here such thing are not happening. So if I say these are two matrices, okay, so now there you have to prove what is that. Yes, you have to, if it is so you have to prove x is equal to b minus a. Okay, this has to be, this is also following the algebraic rule of the equation. So if x is a matrix, so as you know, if I deduct the same matrix, means identical matrix, not identity matrix, identical matrix. So then a minus a, if we deduct, so any matrix you take of same order, 0 0 0 means 2 3, and if I deduct it from the same matrix, so the result will become how much? 0 0 0 and 0. So you will get a null matrix always. So this having no existence, rather, and for equation, you know, we have to do the same exercise on the both of the side. So when you are deducting minus a matrix, a matrix from this side, you have to deduct a matrix from this also. So as you know, for example given, so ultimately this value is become 0, or this has no existence as a matrix. So result will become, so this can be easily proved. So for matrix also, this also follows. Similarly, 2. So in case of 3x is equal to a, if I say, now x is a scalar for this matrix. So if we divide this matrix by 3, and the same thing we are doing, means we are multiplying with 1/3 further of the scalar. So now this is a numerical solution. 1/3 into 3 is a numerical, that is not involved in the matrix. So this can be nullified and taken as x, whereas this is a scalar for this. So this is true for this kind of equation where matrices is act like a algebraic equation. Okay, so this also true. So this can be said okay for matrices. So this kind of mathematics or calculation you can involve in matrices where you are only working with a scalar. So scalar will not change the matrix itself. It will multiply the matrix in a same order. That means if 3 of a matrix is equal to 3 times higher matrix we will get. So that is the only changes. So the value wise when we will expand the matrices we will get the result same. If we do 3 and if I expand the matrix X individually and if we involve the scalar inside the matrix and then expand, then you will get the same result. So this is true for matrices. Okay, so I will end up here today. In the next next video I will start from number 7. Okay, so thank you for now.